Okay, students. Now we'll see case 2. What is case 2? Now case 2 is the reference input. I just take it as a unit step input. Now this is the unit step input. Now what is R of S? R of S, which is nothing but the Laplace transformation of u of t, which is equal to 1 by s. But what is the response? Now C of S, which is equal to R of S into 1 by 1 plus tau s, right? Now this is the reference input, which is a unit step input, right? Now this is the reference input. This is a unit step input. So now R of S is nothing but 1 by Cs. R of S is 1 by S into 1 by 1 plus tau s. Now this is nothing but C of S. Now this is the closed loop control system response. This is the closed loop control system response. This is the unit step response. This is the closed loop control system response, and this is the unit step response. Am I not? Because this is the response after applying unit step input. Okay, but I want the time domain analysis. Therefore, you want to apply the inverse Laplace transformation. You can get the time domain analysis. Okay. Now C of S, which is equal to, can I write like this? 1 by S minus tau by 1 plus tau s. Or you do the partial fraction also same. A by S, B by 1 plus tau s. A is 1, B is minus tau. Or you do the LCM. 1 plus tau s minus tau s cancel. 1 by S into 1 plus tau. Therefore, C of S, which is equal to 1 by S minus, if you take tau as a common here, S plus 1 by tau. Tau cancel. Therefore, C of S, which is equal to 1 by S minus 1 by S plus 1 by tau. 1 by S minus 1 by S plus 1 by tau, and apply inverse Laplace transformation. Apply inverse Laplace transformation. Now see, C of S, which is equal to 1 by S minus 1 by S plus 1 by tau. Then if you apply the inverse Laplace transformation, now this is the closed loop control system response, or this is nothing but a unit step response, right? This is the unit step response in time domain. This is the unit step response in time domain. C of t, which is equal to inverse Laplace transformation of 1 by S is 1 minus 1 by S plus A is e power minus at. Now this is the unit step response or closed loop control system response in time domain. Now this is the response, which is nothing but, this is now if in this response, then I am asking you one question. Then you identify the transient and steady state term. You can easily say that this is the constant magnitude for all the values of time. This is nothing but the steady state term, and this is the time when t tends to infinity. Now this value will become 0. Therefore this is nothing but transient term. Now the time response consisting both transient term as well as steady state term. Am I not? The time response consisting both transient term as well as the steady state term. But in previously, the time response consisting only transient term in the case of impulse. In the impulse response, it consisting only transient term. There is no steady state term in the impulse response. Am I not? So only transient term. Therefore, there is no steady state analysis. But this is the practical response. Now this is the reference level. Therefore, this response is having both transient term as well as the steady state term. Therefore, you have a complete time domain analysis in the case of unit step response or a step response, students. Okay. Anyway, we will draw the response and you can have a complete idea. Okay. Now this is the unit step response, and again you can see here This is the transient response. The transient response is always depends upon system time constant tau. The transient term or a transient response, the actual response is always depends upon the system time constant. And here you can easily understand that the total time response consisting both steady state term as well as transient term. So we'll have both transient state analysis as well as a steady state analysis in this particular practical response. Okay, the practical response is having both transient response as well as the steady state response. Therefore, it is having both steady state term as well as the transient term. So it is having both the steady state response and transient response. This is the practical response, and this will give the total time domain analysis. Okay, we will see the response and with respect to time and see the behavior of unit step response compared with the practical impulse response. We will see. Before that, first you take a copy of this. Okay, now we'll draw the time response, because this is the practical response. Now this is the closed loop control system response, and this is the unit step response in time domain. Okay, now we'll see the response. Now this is the response with respect to time. But there is a reference level here. There is a steady state level. There is a goal here. There is a target here. But if you just compare with the previous response, is there any reference level in the previous cases? Is there any standard steady state level in the previous cases? No, there is no steady state level. There is no reference level in the previous cases. But this is the steady state level or reference level, because this is the practical response. Now see here, this is the steady state level or reference level is available. Whenever the steady state term is available, definitely there is a chance of finding the error analysis. Okay, right. Anyway, now when t equal to 0, now the unit step response, which is nothing but 1 minus e power 0, 1 minus 1, which is equal 0. Therefore, now this practical response, when t equal to 0, it starts at rest position. Right. Now what is the time constant here practically? When t equal to 1 time constant, now the response, which is equal to 1 minus e power minus t equal to 1 time constant cancel, e power minus 1, 1 minus e power minus 1, which is equal to 0.63. Now what is the meaning of that? Now this is the rest position, this is the 100 position, this is the 50 position. Now the time taken by the response to reach 63% of final value is called as one time constant. Now students, you just understand the previous time constant definition. Previously also I am giving one definition. Now that is the time constant definition in the theoretical response, which is nothing but the impulse response. In impulse response, what is the time constant definition? The time taken by the response to reach 37% of initial value, because there is no reference level in the case of impulse, but there is a reference level, there is a steady state level, there is a steady state value, there is a steady state goal. Therefore, the response will reach 63% of the final value is called as one time constant. This is the practical definition of the time constant, students. This is the practical time constant definition. This is the practical time constant definition. The time taken by the response to reach 63% of final value is called as one time constant. Okay. Now similarly, now the time is infinity. When time is infinity, now the response C of t 1 minus e power minus infinity 1 minus 0, which is equal to 1 or 100%. Now the response will reaches to the final value. The response will reaches to the final value with a time of infinity. How much time it will take? The response will take infinity. Now students, you see here, the response will take infinite amount of time such that the response will reach to the final value. So here it will take infinite amount of time. It will take infinite amount of time. Then only this response will reach to the final value. Now I am asking one question. Can you interested to wait infinite amount of time the response is reaches to the final value? No, we are not interested infinity amount of time. Who will wait for infinite amount of time such that the response will get 100 out of 100? No, I don't want, sir. So this is the theoretical value. This is the theoretically. Now this is the theoretical time. Theoretically it will take infinite amount of time such that the response will reach to the final value. No, sir, I don't want 100 out of 100. 95, 96 or 97, it is sufficient for me. So, which means that now practically when t is equal to 5 time constant, now see here, when t equal to 5 time constant, now see the response C of t 1 minus e power t equal to 5 time constant. 5 time constant by time constant cancel, e power minus 5, which is equal to, this is 0.99, which is nothing but 99.99%. Now out of 100%, I can reach 99.99 means, what is the deviation? 1 minus 0.999 means 0.00001. Error is 0.001 means approximately 0 error. This is the practical. This is practically how much time the response will reach to the final value within a time of 5 time constant. This is theoretically. Okay, I don't want this, I want this. Okay, so practically the response will take 5 time constants. Practically the response will take 5 time constants and it will reach 0.999 and the reference level is 1 and response is reference value, final value is 1 and I want to reach 0.999, which is nothing but error is 0. Am I right or not? Now this is the practical time the response will take to reach the final value within a time of 5 time constant. This is very important, student. Any practical response, I am talking about a practical, pure practical response, closed loop control system response. A practical response is nothing but unit step response or a step response. Now only the difference is unit step response is nothing but magnitude is constant and which is equal to 1. Step response is nothing but magnitude is constant and which is equal to some k. It may be 10 or 20 or whatever it may be. If k equal to 1, then that is called as a unit step response. Understand or not? So any response will reach to the final value. Sorry, any practical response will reach to the final value within a time of how much? 5 time constant. Now within a time of 5 time constant, this is called as settling time. This is called as settling time. The time taken by the response to reach final value means with a time of 5 time constant with error of 0. This time is called as settling time, which is TS seconds. Okay. Now I write one question here. Now the settling time TS. Now here itself I can write. Now the settling time TS, which is equal to 5 time constant with error of, how much error? 0% error. 1 minus 0.999 means 0.001, approximately 0. Now, but every time error 0 is not possible. Now sir, how much errors are acceptable? What should be the acceptable error bands? Okay, so the acceptable error bands are 2% error and 5% error is acceptable. Now this is the settling time if error is 2%, and this is the settling time if error is 5%. Now, if error is 0%, settling time is 5 time constant. If error is 2%, settling time is 4 time constant. If error is 5%, settling time is 3 time constant. Okay, these are the acceptable error bands. So 2% error, how much is settling time? 5% error, what is the settling time? 0% error, what is the settling time? And practically the settling time for any practical response is nothing but 5 time constant. The time taken by the response to reach 5 time constant such that the error will become 0. This is the practical definition of the time constant. And if you observe here, the settling time is always depends upon system time constant. The settling time is depends upon depends upon time constant. The settling time is depends upon system time constant. Note down the student. Okay, students, then this is the practical response. Now this practical response, this is the actual response after applying the input. This is the transient response. Now in this transient response, we will find some time domain specification. Now which we already find one time domain specification. Now this is nothing but settling time. Now this is the time domain specifications. Time domain specifications. Now in this time domain specifications, now which we already finished one time domain specification, which is nothing but, what is the one time domain specification? Which is nothing but settling time. Then we will see the another one, rise time. Okay, now we'll see the rise time is another time domain specification. So then what is the rise time? Now this is the practical response. Therefore we can find all the time domain specification. Okay, before that, then here one important point I want to say, time constant definition. What is the time constant definition? The time, note down the students, the time taken by the response to reach 63% of final value is called as one time constant. This is the practical definition of time constant. What is the theoretical definition of time constant? In the impulse response, the time taken by the response to reach 37% of initial value. Okay, right. Now what is the rise time? Sir, how we can calculate the rise time? Yes. Now what is the rise time? First you want to find what is the rise time. Now you first note down the definition of rise time such that you can easily have a derivation for that. The time taken by the response, the time taken by the response to rise from, the time taken by the response to rise from 10% to 90%. The time taken by the response to rise from 10% to 90% is called as rise time. So what he's saying is the rise time is nothing but the time taken by the response. This is the response, right? Now in this response, the time taken by the response to rise from where 10%. Now let us assume this is T1 to 10% to 90%. Let us assume this is T2. This is 90%. The time taken by the response to rise from 10% to 90%. This is the 10% to 90%. This time is called as a rise time TR, which is equal to T2 minus T1. What is this? Now this is the rise time TR. How much it is? And this is the settling time. Right? So now we have a derivation you can easily have. Now this is the response will reach 10%, the time is T1. This is the response will reach 90%, then the time is T2. Right? Now here itself I can do the derivation part, which is very easy. No? This is the time response with respect to time. Right? Now see here. Now this is the response will reach 10%, 1 minus e power minus T1 by tau. Now this is the response will reach 90%, 0.9, which is equal to 1 minus e power minus T2 by tau. The response is 10%, time is T1. The response is reaches to 90%, time is T2. Now find T1 and T2 values here. Now e power minus T1 by tau is nothing but 1 minus 0.1 is 0.9. E power minus T2 by tau, which is nothing but 1 minus 0.9 is 0.1. So this is T1 minus T1 equal to tau into natural logarithm of 0.9 minus T2, which is equal to tau into natural logarithm of 0.1. So now here T1, which is equal to 0.1 tau, minus cancel. Now T2, which is equal to 2.30 tau. That is T2, this is T1. But what is the rise time? The rise time TR, which is equal to T2 minus T1. Now which is nothing but 2.3 tau minus 0.1 tau, which is equal to 2.2 tau. Then you understand. Now as I just explain one simple problem, students. RC network, RC, R resistor, C capacitor, means which order? Yes, first order. Okay. Now for a first order RC network, what is the rise time? You already studied 2.2 times of RC. 2.2 times of RC is the rise time definition. Am I right? Now similarly here, now this is also a first order system. Rise time is 2.2, but don't write RC because RC is also first order. Here this is tau is system time constant. This is the rise time for a first order system, and I am giving the derivation part also. Not derivation is not required for the GATE examination, but you just remember this formula. This is for the first order system rise time, and settling time is for anything. For any practical response, the settling time will be same. Okay, note down this one. Okay, student. Now this is the time domain specification, settling time, and this is rise time. Okay. Now we'll see the time domain specification, which is delay time. Right. Now what is delay time? The time taken by the response to reach its final value is settling time. To rise from 10% to 90% is called as rise time. But what is the delay time? Okay, then that is definitions will never change whether it is a first order, second order, or anything. Only formulas will change because the system is changing. Okay. Now the time taken by the response, to reach 50%, the time taken by the response to reach 50% is called as delay time. The time taken by the response to reach 50% of the final value is called as delay time. Students. Okay. The time taken by the response to reach 50% of the final value is called as delay time. Now this is the response. Okay. Now how we can do the derivation for this? This is the response will reach 50%, which is equal to 1 minus e power minus t by tau. Then you find the time. Now that time is nothing but the delay time. Okay. But for a first order system, there is a relation. For a first order system, the delay time and there is a relation between rise time. Now the delay time and rise time is nothing but for a first order system, this is the actual derivation. The delay time, which is approximately 2/3 of the rise time. The delay time, which is nothing but approximately 2/3 of the rise time. Okay, for first. Otherwise, you can do the derivation part of this. Then that is approximately of this one. Okay. So the delay time, whatever you are answer getting, and simplify that answer and use this formula for a first order system. I am saying now will be approximately same. Therefore, the delay time is approximately 2/3 of the rise time for the first order unit step responses. Okay, for the first order unit step responses. Now, what we can understand, if you understand all these parameters, settling time, rise time, delay time. Now, first we want to find the system time constant. Now, what is the settling time? Settling time is settling time is 5 time constant for 0% error. Rise time is 2.2 time constant. Delay time is 2/3 of rise time, which is nothing but 2/3 of rise time is 2.2 times of time constant. Then what you can understand here, all the time domain specifications is depends upon system time constant or not. All the time domain specifications is depends upon system time constant, because all the time domain specifications which you are finding from, this is the transient response, am I not? This is the transient response. All the time domain specification which you are finding from the transient response, and you already know that the transient state analysis or a transient response is depends upon system time constant. Understand or not? Now I hope you understand this one. Finally, the transient state analysis is depends upon the system time constant, and this is a proof for that also. Okay, but these are the time domain specifications for the first order system. Now similarly for the second order system, definitions will be same, formulas may be changed. Okay, because the order is changing, then all the poles, location and everything will be changed. Okay, these are the time domain specifications of a first order system, and this is the transient state analysis. But this response is having a reference level. You can measure the error at each and every instant of time. Therefore, now we will do the steady state analysis of a first order system, such that we will finish the total time domain analysis of a first order system. Note down this particular derivation part, such that we will go for the steady state analysis of a first order system, student. Okay. Then we will see the error analysis. Steady state analysis. Error analysis means what? Steady state analysis, because whose role is to find the steady state analysis, error and calculation of error and steady state error. The calculation of error and steady state error role is a steady state analysis job. So we will find the steady state analysis, because this. Now you tell me, is there any scope of finding the steady state analysis? Yes, here the scope of finding steady state analysis, it consisting both transient term as well as steady state term. This is the transient term and this is the steady state term. It is having both. The total time response is having both transient term as well as steady state term. This is the transient term and this is the steady state term. It is having both transient term as well as steady state term. So you can find the steady state analysis also, right? Now students, now what is the error? You know that. What is error? Error is the deviation of. Now see the block diagram. Now this is the forward path gain. This is the feedback path gain. Now this is C of S. This is R of S. This is E of S. Error. You know that. Error is the deviation of output or processed output from the reference level. Is it right or not? What is error definition? Error is the deviation of output or processed output from the reference level R of S minus C of S. This is C of S, this is R of S. But I want in time domain, therefore apply inverse Laplace transformation, therefore E of t, which is equal to R of t minus C of t. This is the error definition. This is the error signal. The error signal is nothing but the deviation of output or processed output from the reference level. Am I not? Now, can you find the error? Now, this is the steady state analysis of a first order system. Now, what is error signal? E of t, R of t. What is R of t? See here, R of t is the reference input, is the unit step input whose magnitude is constant. 1 minus, what is C of t? C of t is the closed loop control system response or a unit step response, which is nothing but 1 minus e power minus t by tau. We already finished that, right? 1 minus e power minus t by tau. So 1 cancel. So minus minus plus. This is the error. Now see here, this is the error. Now which is measured at t1 seconds, at t2 seconds, at t2 seconds, everything you can measure, okay? Now the deviation of output, see here, the deviation of output from the reference level, this deviation is called as error E1 at t1 seconds. This deviation is called as error E2 at t2 seconds. This deviation is called as error E3 at t3 seconds. Now you can scope of finding the error at each and every instant of time, because there is a reference level here, there is a steady state level, there is a reference level. Error is the deviation of output from the reference level. You can measure the error at each and every instant of time. Based on the error, you can judge your system performance. Am I not? Now this is called as error. No sir, I want steady state error, sir. What is steady state error? What is steady state error? The steady state error. Now this is error. Now what is the steady state error? Sir, what is steady state error? If you measure the error, steady state error is nothing but, this is ESS, steady state error. Now the students, I am asking one question, without any calculation, how much error you are expecting? Steady state error is the error at t tends to infinity, is nothing but a final error. Steady state error is the error. Steady state error is the error at t tends to infinity. Students, if you calculate the error at t tends to infinity, that final error is called as steady state error. Like see here in the response, t1 seconds, t2 seconds, t3 seconds, t4 seconds, t5 seconds, like that. What is the final error, sir? What is the final error of this particular response? That final error is called as a steady state error, represented by ESS, steady state error. Okay. If you measure the error at t tends to infinity, is called as steady state error. The final error is called as steady state error. Students, I am asking one question. Now finally means if you take infinite amount of time, definitely the response will reach to the final value or not? Yes, obviously the response will reach to the final value. Therefore, limit t tends to infinity. What is E of t? E of t is nothing but e power minus t by tau. So t tends to infinity, e power minus infinity is 0. If you measure the error, if you calculate the error at t tends to infinity, now the steady state error is the error at t tends to infinity. If you calculate the error at t tends to infinity, now that error is called as steady state error. If you find the error at t tends to infinity, now that final error is called as steady state error. Now without any doubt, now if you take infinite amount of time and the response will reaches to the 100% or final value, then error is 0. Yes, this is the practical response. This is the practical analysis. Then there is a scope of getting a 0% error, then you will take a time of infinite. No, no, sir, you are saying that practically infinite time constant is not possible. That is only theoretical. Yes, practically also I am saying, if practically if you take this t as a 5 time constant, this value is very small value. 0.001 means approximately the error should be 0. Am I not? This is the error and this is the steady state error. Now this is the job of role of steady state analysis. Students, I am asking, now this is the time domain analysis of a first order system and a complete time domain analysis, because which will cover both transient state analysis as well as a steady state analysis, because this response itself is having a steady state term and is having a transient term. But now the students, if compare with the impulse response, in the impulse response you don't get any steady state term. The impulse response consisting only transient term, and there is no chance of finding the error and steady state error analysis in the case of impulse. That is the difference. That's why that is called as a theoretical response. Theoretical analysis we always go for impulse, but for practical analysis we go for unit step and step. Understand or not? Now this is the theoretical, this is the practical analysis. And this is the complete time domain analysis of a first order system, which include both transient state analysis and which include as well as a steady state analysis. Okay, now note down the students. Okay, this is the way generally calculating the error. Error is the deviation of output from the reference level, and that deviation is nothing but the error signal, and the last error, the final error, is called as a steady state error. Okay, if you measure the error at t tends to infinity, is called as steady state error. If the error is the deviation of output from the reference level, is called as an error signal. Okay, note down the student. Now the students, now this is case 2, which is nothing but unit step input. Previously we just see the impulse input, now unit step input. Now there is another inputs are also available. Some other unbounded inputs, some other theoretical inputs are also available. Now that theoretical input is nothing but the ramp input and parabolic input, but practically it is not useful, but for theoretical calculations we just go through once. Okay, for theoretical calculations we just go through once. Now we'll start with case 3. Now unit ramp input. Unit ramp input. R of t, which is equal to 1 into t. Now this is the linearly varying input, which is an unbounded input. Slope is 1 unit. Therefore, R of s is this is 1 by s square. R of s, which is equal to 1 by s square. Now C of s, which is equal to R of s into 1 by 1 plus tau s. Now R of s, now the reference input, which is nothing but 1 by s square 1 by 1 plus tau s. Now this is C of s, now which is nothing but, now students, this is the closed loop control system response. This is the closed loop control system response. Therefore this is nothing but unit ramp response. This is the response after applying unit ramp input. Therefore this is the unit ramp response. Okay, but this is in frequency domain. Then if you want to do in the time domain, apply inverse Laplace transformation and do the partial fractions first. Do the partial fraction a by s, b by s square, c by, and after that a, b, c values calculations and apply inverse Laplace transformation. This is the lengthy method. Okay, there is no need of doing this one. You have some shortcut method, use that one. Why unnecessarily you are doing all this lengthy analysis, partial fractions, a by, b by, c by, partial fractions, all these things are not required. So you just have some shortcut method, use that one. Now my students, I am asking, just now you finish time domain analysis of first order system. For the same first order system you have a unit step response. What is the unit step response? This is the unit step response. This is the unit step response in time domain. What is the unit step response? C of t, which is equal to 1 minus e power minus t by tau. This is the unit step response. Student, this is the unit step response in a first order system. But I want a unit ramp response in time domain, right? I want a unit ramp response. You have one relation between unit step response and unit ramp response. I want unit ramp response. The unit ramp response in time domain directly is integration of unit step response. Integration of unit step response. The unit step response. If you integrate the unit step response for all the positive values of time, then you can get the unit ramp response. Therefore, which is nothing but integral 0 to t 1 minus e power minus t by tau into dt, then directly you can get the unit ramp response. Now students, you just do this integration and you can get the unit ramp response directly from the unit step response. Okay, that is the direct answer why unnecessarily we are doing this one. Okay, you just do that one and you can take a copy of this.